So, welcome everyone to our second of our seminar and training skills series that we're doing. Our first one was just over a month ago with Matt Streets from Rollwater, who gave an introduction to life, transitioning into life as from academia to non-academia to industry. And today we're absolutely delighted to have two researchers from the University of Edinburgh joining us. So Casey-Ann Hoog and Christina Talavera Rodriguez. But first of all, before we go to them, I'd just like to give a little bit of an overview about the Mineralogical Society. So my name is Emer Didi, and I'm the General Secretary of the Society. And the MinSoc, which is of the UK and Ireland, was founded in 1876, so we've been around for quite a long time. And one of the main things that we do actually is publish things. So we have three different journals now, a very new one in geobiointerfaces, and our very long established Mineralogical magazine and Clay Minerals, which you may already know of. But we also publish quite a lot of books, mineralogical books. So the rock forming minerals. We have, although of course we have our MinSoc Council, we're actually we sit over a whole pile of special interest groups, and these are a really wide range of different mineralogical applications, I guess. We have our applied mineralogy group, clay minerals, environmental mineralogy group, geochemistry group, geomicrobiology group, metamorphic studies, mineral physics, and volcanic and magmatic studies group, also known as VMSG. Some of these we sit between ourselves and the Geological Society, but this is really where most of our members sit, and that is how mostly people get involved through activities and events that are run by our SIGs. So today, like I said, we've got Casey-Ann and Christina from University of Edinburgh, who will be talking to us about the ion probe. And like I said, Matt Streets presented in October, and you can see the recording of that on our website, which the website is just there. For 2025, we already have a program in place. John Faithful should be delivering a workshop or a seminar on asbestos and asbestiform minerals in January. Some of my colleagues at the BGS then will be delivering a range of presentations, one around the scanning electron microscope. Diana is going to give an overview on the NEEF scheme, which is how you actually apply to get isotopic work done through NERC central facilities. Then Nick Roberts, who I think is probably on the call, is going to present on carbonate dating. And then we have colleagues from the OU and Diamond who will also be presenting on different techniques later in the year. So we hope very much that you will join us for some of those. And then finally, if you're not a member already, we would love to welcome you. We actually have a new scheme where the first 3 years of student membership is actually free. So if you are a PhD student and are not a member, please do come along and join us, or undergrad or masters. We'd love to have you. And then we have a very reasonable rate of £19 per year during your student years. And then our ECR membership, at the moment, we're just getting all this through council, and we will have a discount rate coming early in 2025, so you might want to hold off but join us please next year. And then generally our membership is quite reasonable at £55 a year. That gives you free access to our journals, membership of our special interest groups or multiples of our special interest groups. It allows you to apply for bursaries for travel and research, and we've got a whole host of awards that we give out annually that you could get involved with and nominating or being nominated. You'll get a free subscription to Elements, you get discounts of books and reduced registration fees for big conferences, including Goldschmidt, as part of that partnership we have with a whole pile of European surveys, other European surveys. So I think that is my last slide, and I would that's it. And I would very much like to welcome now Casey-Ann and Christina to start presenting. Thank you all very much.
So my name is Casey-Ann Hoog, and next to me is Christina Talavera Rodriguez. And we're both at the Edinburgh Ion Microprobe facility. And we have a third colleague, Jens Barosh, who's not in this meeting, but the three of us, we run the facility. So in this talk, I'll start with presenting some background about the instrumentation and some applications. And Christina, we need in the meantime to go back to the lab, which is the life of running ion probes, we'll then continue with some more information about access to this facility and sample preparation, I believe.
Yes.
Right, okay. So I'll see you soon.
Yeah.
So yeah, so briefly, so we're at a facility. We're a NERC-funded facility, or partially NERC and partially by the University of Edinburgh. You have two ion microprobes, a Kamika 1270 and a 7FGO, and I'll explain later what that means. Basically, we provide SIMS analysis to researchers worldwide, including NERC-funded researchers who can apply basically for the analysis for free through the IMF steering committee, and other funded researchers can use pay-as-you-go route to access this facility. And we've been running this, well, not us, some of our older colleagues since 1987. We do about 20, 30 projects a year, which are all generally about a week long, although they can vary from a few days to several weeks. And about 50% of our user base are PhD students. And we have a lot of information on our website, which you can access through this link, and presumably later when you can download this presentation. So SIMS, or secondary ion mass spectrometry, what it's called, is maybe a less well-known technique. So most people probably are familiar with electron microprobes, SEMs, maybe laser ablation, ICP-MS. But SIMS is not something you might come across, certainly not early in your career or as a student. So it's a microanalytical technique. And it's a very versatile technique, which you can use for trace element analysis, isotopic analysis, use it for geochronology. You can also do depth profiling. Depth profiling is actually what the instrument more or less was designed for, because that's used a lot in the semiconductor industry, which is actually the largest user of ion probes. It can also be used for imaging, and for that, people might be more familiar with the nanosims, which is an even smaller scale version of a SIMS, a smaller resolution, which is mostly used for imaging. So some features of SIMS. So just to clarify, we also call it ion microprobe. So ion microprobe really is sort of the instrument itself. And SIMS is the name of the technique, but they're used interchangeably. So with SIMS, we can do elemental concentration and isotope ratios at a micrometer scale. And we can basically use any element in the periodic table that ionizes from hydrogen to uranium with the exclusion of noble gases. Our detection limits are generally ppm level, but they range sort of from ppbs to percent for some elements. It requires minimal separation, sample preparation, but we need a polished surface. The analysis itself is almost non-destructive because it's at a very small scale and goes very shallow depth into the sample. As said, it's a very high spatial resolution. And this allows us to analyze in situ, for instance, scale growth zones and complex textures. We can analyze, for instance, fin sections or other materials. We can integrate elemental and isotopic analysis sometimes at the same time. And we can use a wide range of matrices. So we generally in our lab mostly work on minerals and glasses, but we've done work on bones and teeth and wood as well. Some drawbacks is that samples need to be vacuum resistant. It's relatively slow compared to laser ablation ICP-MS. Most of our analysis take between 4 and 20 minutes. And it's a comparison technique, so you do require calibration standards. So these are two instruments. So we have what we call a small geometry and a large geometry instrument. So this is the small geometry instrument, and that's the large geometry one. The 7F Geo was installed in 2018 to replace the 4F, which was an older version, and that was the first instrument that we have that was installed in 1987. The 1270 was installed in 2003, and it's becoming very long in the tooth at the moment. It's actually the only surviving running 1270 in the world, at least in earth sciences, as far as we're aware. But the good news is that we will be able to replace it soon. So our 7F was installed a few years ago. One of the major upgrades on that was that it had a new oxygen source, which allowed us to work at even smaller resolutions with higher beam currents. It also allowed automated access, and it had a better magnet, so we can do better high resolution work. I'll come back later what that means. Now, the brilliant news for our lab is that our 1270 is going to be upgraded next year to a Kamika 1300, which is the newest instrument. And it will be the first Kamika 1300 in earth science in Europe. And NERC paid it for us. So this instrument will have a brighter and more stable oxygen source, which we already have on the other instrument, but not on our old 1270. It has an improved multi-collector detection system, and it will also have automated sample exchange and better remote access. So it should allow us to work much more efficiently. We have actually some 3D sort of models, images from our lab, which you can access through this link. I won't click on it now, but basically you can zoom in on different features and get explanations. So if you're interested in our different instruments, you can have a go at these links at a later time. Right, some background about ion probe and how it works. So this is a schematic diagram, and essentially it's we have different components. We have what we call a primary column here. We have a secondary column, which is essentially this whole part here. We have a mass spectrometer, which is this part, and then we have a detection system. Now, in the primary column, first of all, we have two sources of ions, and we generate primary ions. And this primary ion beam is accelerated down this column and then focused onto the sample, and then the ions hit your sample. That then knocks other ions out of the surface of the sample, and those ions are accelerated into the mass spectrometer. And that's called a secondary ion beam, and therefore the technique is called secondary ion mass spectrometry. So these secondary ions go down the mass spectrometer and are then separated based on their mass, and then detected here by an array of detectors, depending on the application that we were interested in. So the mass spectrometer design is quite similar to TIMS and magnetic sector ICP-MS. The front part is maybe more comparable to an electron microprobe because instead of electrons, we have an ion beam, but it's focused onto the sample in a similar way. So the primary beam basically hits the sample. As you sort of can see here, the primary beam is coming in. It's actually coming in at an angle, which is important because height variations therefore lead to some movement of the beam. So you'd like samples to be as flat as possible. But this knocks ions out of the surface, but actually not just simple ions. It actually knocks out a lot of very complex a complex mixture of positive ions, negative ions, electrons, oxides, and various molecules. And we'll come back to that later why that is important. So this is a typical ion probe pit. It's actually quite a deep one because these were several analyses that were done on the same spot in a row. This was a small melt inclusion. And you can see here the scale is 10 microns, so that's roughly the size of the beam that was used. Now we can change the beam size by increasing the beam current, but that means then, so we get more beam current, you get more signal, but the beam also gets bigger. So if you want very high spatial resolution, you need a smaller beam and you get less signal. So it is a so they counteract each other. So for the primary beam, you have two different sources. And one is essentially composed of negative ions. So that's an oxygen source. And the other one is positive ions, which is a cesium gun. And generally we use positive ions to measure negative ions and the other way around. So for elements that are best ionized as negative ions, so such as halogens and sulfur and oxygen, we use a cesium gun with positive cesium ions. And for most other elements that are ionized as positive ions, we use the oxygen source, the negative oxygen ions. So here on this periodic table, you can see which elements are generally analyzed with which source. There are two different setups, so you can't analyze both at the same time. So we can't run the cesium gun and the Hyperion at the same time. So if you need a range of these elements at the same time, it might mean that you need to have two sessions of analyses. So the difference between our small and our big instrument, because you might wonder why we have actually two. So the small geometry instrument, the 7F Geo, has quite a small footprint like this. It's about, well, it's a couple of meters wide. And if you compare it with the 1270, it's much, much larger. The front end is actually the same. So this part here is more or less the same, but it's this part, the mass spectrometer part, which is much, much larger. So the smaller instrument is great because it has a fast magnet, it has a single detector, and it's very suitable for trace filament analysis. The large instrument also has a multi-collector array, and the larger geometry of the mass spectrometer means you can get higher mass resolution. And that's ideal for isotope ratio analyses. And it's sort of explained here. So here we have the primary beam hitting the sample, then the secondary beam is going into the mass spectrometer. And then because the 7F has a smaller geometry, you just get less dispersion of the same isotope as you would have it in the 1270. So, and that's the reason why you get higher mass resolution on the large geometry instrument. And that allows you to separate different molecules and ions that are very close in mass. There's a number of things to consider for ion probe analysis. So one of them is interferences. So we get a lot of molecular ions with the same nominal mass as the analyte we're interested in. There might be matrix effects. So the major element composition of the sample might give a strong bias. And this is actually poorly understood because the same happens, for instance, in EPMA, electron probe, but there is a good physical model that can make corrections. And for ion probe, we don't have that. Availability of standards can be a problem because they need to be matrix matched. So they need to be closely and compositionally similar to the sample that you're analyzing. And they're not always easy to obtain. And they can also not necessarily be homogeneous. So they need to be tested for any heterogeneity. And then the sample requirements, samples need to be compatible with an ultra-high vacuum. We work at about 10 to the minus 9 millibar. And samples need to be gold-coated if they're not conductive, which is true for most geological materials. So about these interferences, which is sort of the main issue we're dealing with ion probe, it's so if we hit the sample surface with our ion beam, we knock out a lot of ions from the surface, and they often recombine to form complex molecular interferences. So for instance, if you're interested in measuring calcium on mass 44, you might have a number of other ions that are interfering with that, with the same mass. For instance, silicon oxide, strontium 2 plus, calcium hydride, all those are present in the spectrum. And we have various ways of dealing with that. In fact, there's three ways. One is increasing mass resolution, the other one is energy filtering, and a third method would be peak stripping. So high mass resolution. So essentially what you do is that you increase the mass resolution of the instrument, and thereby you separate ions that are close in mass but not identical in mass. So for instance, for oxygen isotopes, here we have a 17 oxygen peak, and then we see next to it is a 6 oxygen hydride. So to separate those, we need a mass resolution of about 6,000. Now, getting higher mass resolution has a drawback that you also start to lose intensity. And generally, you try to get as much signal as you can get, because that gives you higher precision analyses. Now, on the 1270, the 1280, and the 1300, so the large geometry instruments, the base resolution is already about 4,000. And then the intensity slowly decreases by increasing the resolution. Whereas on the 7F, this occurs much more rapidly. So you start losing intensity basically at a fairly low mass resolution. And this is why, if mass resolution is important, we prefer to work on the 1280 or the 12, well, currently our 1270. A second way of reducing interferences, which is better to use if you work with if you're analyzing many different elements at the same time, is energy filtering. So the ions that come off the surface, they have a certain energy, and there's actually they come off the surface with different energies, and so there's an energy distribution, which peaks at close to 0 volt. So a lot of ions that come off the surface have very little energy. And then there's higher energy ions that have, so they have some sort of velocity. And that's expressed here in this ion energy, this secondary ion energy. And more complex molecules generally decrease much, the energy distribution is much more skewed towards the low energy part. So if we then apply what we call an energy window, we improve basically the signal to noise ratio. And that's what we're doing. So for instance, for silicon, if we apply 75 volt energy offset, as we call that, with this energy window, we lose about a factor 10 in intensity, but any potential interferences, such as oxides and dimers, like you see here, they lose much more of their intensity compared to the isotope that you're interested in. So that reduces the interferences. And it also tends to reduce matrix effects, which is an additional bonus. And the third way of resolving interferences is by peak stripping. And essentially what you then do is you don't actually try to avoid the interference by, for instance, using high mass resolution. But what you do is you measure another isotope of the same interference, and then you calculate how big that interference is, and then you subtract it from the original, from the total signal, and it then leaves you with the analyte that you're interested in. So in this case, with the example with silicon oxide interference on calcium. You can still use this as well in addition to energy filtering, and often we do that for certain elements that are where we still have significant interferences left despite the energy filtering. Okay, so I guess by now you're aware that these interferences are quite complicated problems, but there's different ways of dealing with them depending on the specific application that we're using. And one more thing to point out is that different ions ionize at very different rates. So on this diagram, what you see is basically a periodic table of all elements, and their relative ion yield is on this axis. It's a log axis compared to silicon. So silicon is 1. And then you can see how well these ions ionize relative to silicon using as positive ions. So you see, for instance, rare earths ionize very well, but for instance, halogens ionize very poorly, and actually, for instance, lead and cadmium and zinc. So some of the transition metals also ionize quite poorly. Now we can use negative ions, and then actually this image is not quite reversed, but more or less reversed. So then these elements, the halogens, for instance, ionize very well. So if we use the cesium gun or the oxygen source, it's sort of dependent on the elements that we're interested in, which ionize the best with which source. And so overall, then that leads to detection limits of in the range of nanograms per grams to milligrams per grams for different elements in positive or either as negative secondary ions, which you can see on this periodic table here. Right, so that was mostly about the technique, and I will jump quickly to sort of the type of SIMS analysis that we do at IMF. And as I said before, ion probe is a very versatile technique. So we do a wide range of different types of analyses with those 2 instruments that we have. So for instance, we do a lot of volatile work, hydrogen, carbon, halogens, and trace elements in glasses and minerals, including normally anhydrous minerals. We do work on carbonates, carbon, oxygen isotopes, trace elements. We do uranium-lead dating of zircons, rutile, monazite, apatite. We do work on diamonds, such as carbon and nitrogen isotopes. We work on sulfides, doing sulfur and iron and sometimes copper isotopes, as well as trace elements. And then there's a lot of different isotope techniques we can apply to silicates, including oxygen, silicon. We do quite a lot of lithium boron, some chlorine, and we have done some limited magnesium and iron isotopes as well, in addition to trace elements. So in terms of isotopes work, those that are major elements, we can generally get precisions down to about 0.2 per mil. That's 1 sigma. And other isotopes are generally about 0.5 to 1 per mil. And uranium lead ages are about precision of about 1%. So I'll go through a few of those in a bit more detail. So one type of sample that we do a lot of work on in our lab, basically because of the demand from the user community, are melt inclusions. So melt inclusions are little bits of trapped melt that have then become glass upon cooling in crystals from igneous origin. And we can do a whole set of different analyses for those, including volatiles, such as water and carbon. Also the elements that ionize better as negative ions, including halogens and sulfur. We can do all sorts of trace elements, but we can also do lead isotopes, boron isotopes, and oxygen isotopes. And if a melt inclusion is about 100 micron, we can actually do all of these on the same melt inclusion, which is one of the most powerful aspects of ion probe. So this is just an example of one of the publications of work done in our lab. So people have done carbon and water analysis on melt inclusions, and they can use that, for instance, to estimate the depth at which these melt inclusions were trapped and look at the volatile evolution of those. So we measure water as hydrogen. So we calibrate. We measure 1H hydrogen, and then we normalize that to silicon. So we generally need an element to normalize to, which needs to have a known concentration. And generally we use silicon because that's relatively easy to measure for us, but also, for instance, on electron microprobe. So for water, we have a good set of standards. There is some matrix effects, but it's not very strong. So this is, for us, it's relatively easy to do now. Backgrounds are not necessarily trivial, so you have to be a little bit careful with, for instance, the mounting of your samples. We need to make sure we have good vacuum. So the backgrounds are sort of between 0.01 and 0.28% water. So if you want to measure water in really water-poor samples, for instance, melt inclusions in morph glass, you might want to consider, for instance, not using epoxy because that tends to lead to high water backgrounds. And the good thing about our setup, by measuring it as H, 1H, and positive mode, as a positive ion, is that we can analyze it simultaneously with many trace elements. So you get water at the same time as, for instance, rare earth and other trace elements that are of interest from sort of a petrological viewpoint. We also do normally anhydrous minerals. So those are minerals that have no structural water in their mineral composition, but they may still have some water in their in the mineral. For instance, orthoparoxene, clinopyroxenes, garnet, olivine, plagioclase. These are all normally anhydrous minerals, but there will always be some water present in them. And we can measure that down to about 5 ppm. So for that, we need some extra precautions because that's a really low water content. And so we need to have a long vacuum pump down, for instance. We might bake the airlock to get sort of rid of water condensed on the inside of the instrument. We mount samples in indium, which is a soft metal, so you can just push minerals, for instance, into there. We need to avoid epoxy at all costs because that always leads to high water backgrounds, because even though epoxy seems hard, it keeps out gassing. We would mount some anhydrous material in the same mount to measure the hydrogen backgrounds from the background, so we get a good background correction. And we need to use dedicated, which means mineral match standards for different minerals. And these are just some examples of calibration curves that we do. We have here ppms of water, and these are calibration curves for different minerals. We also measure carbon as CO2, again, often in melt inclusions. So we have a good set of standards for those as well. These are standards that are made by experimentally in a lab and in piston cylinder experiments. And these bits of glass we use as standards. They're well characterized. And one of the features, though, of carbon is that carbon itself is mass 12, as you can see here, 12 carbon. In basaltic material, you will have an interference of 24 magnesium 2 plus. So any sample that has more than about 0.2 to 0.5 weight% magnesium, so which is a lot of glasses, will actually have an interference that we need to avoid. And the way we do that is with high mass resolution. So you don't need super high mass resolution, only about 1200 to 1600 is enough to basically distinguish these two different peaks. So we would avoid this peak and we would analyze here on this mass, this little shoulder for the carbon. On our new instrument, the 7F, we can actually do water and halogens at the same time at that mass resolution, so which is very useful because we can then analyze all these elements together at the same time from the same volume in your melt inclusion, which is something we couldn't do on our older 4F instrument. So carbon detection limit is now down to about 5 ppm, so it's very low, so we can measure very low carbon content in melt inclusions. One potential issue with carbon is that it actually is almost unavoidable as a contamination of the surface. So what we generally do is we pre-raster the area of a sample before we analyze it with our primary ion beam. So the primary ion beam that we use to analyze, we can also raster it over the surface, sort of to pre-clean the surface. And so we then apply like a 20 micron raster for about 3 minutes, and that cleans any sort of carbon residue from the surface. We're also trying to avoid any irregularities as cracks and inclusions, because that's often where you have carbon contamination, because samples are often mounted in epoxy, and if you don't polish them, you will smear carbon all over the surface. They're often also cleaned with carbon-bearing cleaning agents. And you might also get, for instance, oil mist from the vacuum pumps for carbon coating. So there's always carbon on the surface, and we try to get rid of that with these pre-cleaning procedures. And the fact that we now have detection limits of about 5 ppm carbon or less shows that this cleaning is very efficient. Nevertheless, you don't want to hit the edge of the melt inclusion, such as here, because it's very difficult to get rid of any carbon residue there. And also, if there's any cracks in the surface, carbon might be hiding in there as well. So, so you need a very good a very good polish on the sample surface to do good carbon analyses. Now, I've mentioned stable isotopes, so there's a lot of different stable isotope systems that we can measure. So I've shown some of them here, and also with the main ratio of the elements. Typically, how well you can measure an isotope ratio is sort of determined by the least abundant isotope of the two. So if there's a very large ratio, for instance, H over D of more than 6,000, it means there's very little D present, deuterium. And that makes analysis more difficult because you either need to measure very long or you need a lot of water for it to be able to analyze. Whereas, for instance, boron has two isotopes that are, the ratio is only 4. So, so the weakest link is 10 boron, but it's still, even at low concentrations, there's enough 10 boron for us to get good precision on low boron content samples. So the minimal concentrations for a sort of reasonable analysis time that we need for water would be 1%, but for CO2 only about 300 ppm, and for sulfur and chlorine even lower. So maybe in the interest of time, I won't stand still too long with boron isotopes, but we have done quite a lot of boron isotope lab work in our lab for the last 10 years. It's been used quite a lot in volcanology to sort of trace the volatile content or the volatile sources in, for instance, subduction zones. And this is one of these studies where they essentially found that along the Antilles arc, there's a large variation in boron isotopes in the melt inclusions, which you can see here. And that was interpreted as increased subduction of serpentinize in fracture zones. So as I said, I won't stand still for too long, but we can measure boron isotopes down to about 0.1 per mil for about 10 ppm boron. So we can measure very low constants of boron, we can still get good isotope analyses. And we also do that in minerals. For instance, we can measure boron isotopes in pyroxenes, olivines, amphiboles, micas, and we have good sets of standards for those. A material that we see more and more of over the last few years is apatite, which is sort of like a new kid on the block in terms of volatile analyses. So people start to understand that sometimes melt inclusions have actually some drawbacks. For instance, they might lose their volatiles quite easily. And apatites are more robust in that sense, so they keep their volatiles better. But they're more difficult to interpret. So people have been working on using apatites to say things about volatile emissions from eruptions. And sometimes these apatites are really small. So these are very small inclusions of apatite here, in this case in biotite. So the inclusions are only about, these apatites are only about 10, 20 micron. But with a very small beam, we can still get good volatile analysis of these. So we can measure hydrogen and carbon, fluorine and chlorine and sulfur all at the same time on this tiny spot in these apatites. Now, another big application in our lab is oxygen isotopes. So we do a lot of melt inclusions and we do a lot of oxygen isotopes. That's basically the two main things that we do. And oxygen isotopes, so we apply those to silicates and carbonates, and they need quite a different setup than all the other things I've just shown you for the melt inclusions. So here we use a cesium beam. So we measure oxygen then as a negative ion. But with a cesium beam, we also need electron charge neutralization, because we're hitting the sample with a lot of positive charge. And even though we gold coat samples, they can't get rid of that charge. So we need essentially also an ion beam at the same time, an electron beam at the same time to get rid of that extra charge. We also need to use high mass resolution because of interferences, for instance, of hydrides, 16 oxygen hydride, for instance, on 17 oxygen. Because if you wouldn't resolve these interferences, then samples with different water content would give you different oxygen isotope ratios, even if they had the same ratio. But the analyses are relatively quick, so in about 4 minutes, we get a precision of down to about 0.2 per mil. One of the drawbacks is, though, that oxygen isotope, there is strong matrix effects in complex matrices. So, for instance, carbonates, if you have different magnesium or different iron contents in these carbonates, that will affect the oxygen isotopes. So you need a good set of standards to basically correct for that. And the same applies to silicate glasses and even, for instance, garnets, where you have a large range in compositions with calcium and iron and magnesium, and that requires close matrix matching. So on a new instrument, we'll get some new detectors, which also allows us to do triple oxygen to very high precision. So that's basically the difference between oxygen 17 relative to 16 and 18. So for oxygen isotopes, we use what we call a multi-collector array. And that's basically so you can analyze different isotopes at the same time. So when we do the other elements, we often use a single detector, and then we just hop from one isotope that we want to measure to another, and then to another, and then you go back and you do that several times. But with a multi-collector, you can analyze them at the same time. So for instance, here, this is the multi-collector. We have different detectors on there. And the ion, the secondary ion beam is coming from here, from the magnet. And then the high mass would be here, for instance, oxygen 18. And then oxygen 17 would be in the middle. And oxygen 16 would come down here. And then you would measure those simultaneously. And that allows you to obtain higher precisions. So you would go down from about 0.5 per mil in single detector mode to 0.1 to 0.2 per mil in multi-collection mode. So if you need the highest precisions, that's what we use. So an example of material that we do this on is a fish otolith. So I believe that these are parts from fish ears. It's a biogenic material that grows in fish, and it shows growth rates. So they start growing when the fish basically spawned, and then they keep growing during their lifetime. And sort of like tree rings, and you can measure then the oxygen isotope ratios in those. And so this is a sample mounted with the oxygen isotope pits, and this is then the data. And there's a distinct jump in oxygen isotopes from basically the center of the autoliv to here. And that has been interpreted as having to do with the temperature of the water that the fish were in. So another application is carbon isotope analyses. We do that, for instance, on diamonds, and this is actually an example of ion imaging. So here, what we did is there was a big diamond, several millimeters in size, and then we just did a whole raster over the surface of the diamond. And then we measured the carbon isotopes, and then we plotted that as a diagram like this. So the total range in carbon isotopes was from about -10 to -18, and that's shown here in these colors. So in that way, you get basically a growth map of this diamond. And then finally, a final application of ion probe that we do in our lab is uranium lead dating. So uranium lead dating was the first done on an instrument called a shrimp. And so you may be more familiar with the term shrimp dating. And shrimp was actually an acronym of the word sensitive high resolution ion microprobe. And that was developed at ANU in Australia. And that actually inspired Jamaica to develop the IMS 1270 in the 1990s, which is the instrument we have. And so ion microprobe dating is very suitable for complex zircons that you can't really analyze by dissolving them and then analyzing them by TIMS. Because they have complex growth zones, multiple H domains, so they're especially suitable, for instance, for metamorphic overgrowth. So for uranium lead dating, we use often a 16 double oxygen ion beam. So it's O2, ionized O2. And then there's various techniques such as oxygen flooding to improve the ion yield. So we actually bleed a bit of oxygen in the sample chamber, which increases the yield. We need high mass resolution to avoid hafnium-based interferences. And we need to apply some corrections based on the on uranium oxide to sort of account for the difference in ion yield between uranium and lead. So it's fairly complex to set up, but it works very well. And for instance, you might have seen CL images of zircons. These sort of black and white patterned images in which you see all sorts of different textures, such as growth zones. And in this case, for instance, for this study, we found igneous cores that were about 250 million years old, and then thin rims that were only about 90 million years old. And they could be correlated with ultra-high pressure metamorphism in that area. So, so you plot the data on uranium lead diagrams, and then you get an isochron, and if you're lucky, the samples plot on the Concordia, on the concordant, and then you can work out the ages. So this is nowadays also done a lot by laser ablation ICP-MS, which is sort of a competing instrument. Sort of depends on the application if that's possible for you. Laser ablation ICP-MS is generally cheaper and quicker, but generally it's more destructive. So it depends on the size of your zircons, how much other analyses you might want to do. For instance, hafnium isotopes, which you need to do by ICP-MS, but we cannot do that. But we can do oxygen isotopes, and we can do uranium lead dating. So it depends on those sort of things if you decide to use ICP-MS or ion probe. So this is a typical example of an ion probe pit. I think laser ablation has become better than this by now. So they don't need 5 to 50 micron pits anymore to get uranium lead ages. But still, they generally go much deeper than the ion probe. Okay, so that sort of concludes my part of this talk. So just to summarize, is that SIM is an extremely versatile microanalytical technique, and particularly suited for analysis of volatiles and stable isotopes, as well as age dating. One of the main drawbacks is the need for matrix match standards, but more and more become available all the time. And it's ideal for analyses that are difficult to do by other in situ techniques, such as laser ablation and EPMA, as it is a relatively slow and expensive technique. And if you're interested in more applications that we can do with the ion probe, you can also have a look at the annual user reports that we get for many more applications via this link. Okay, and then I'll hand over to Christina.
So basically, after Keshan introduction about the technique, I just would like to talk a little bit about how to access the facility. The first thing that you need to do is just send us an email to the ionprobe at ed.ac.uk and introduce yourself, give a brief summary of what would you like to analyze, what type of material, precision, and then one of us will contact you and so discuss with you the different routes that we have to get access. There are actually two different routes. The first one is pay as you go, and this route is basically for non-NERC researchers and for researchers that have UKRI grants, FTFC, overseas researchers, commercial work. And then we have the NERC application route. This is for NERC researchers, researchers that have NERC grants, NERC DTP students. So if you decided to go via pay as you go, you need to complete a form that you can find on that link and send it to us. We'll then evaluate and assess the feasibility of your project. If it's possible for us to do it, we will prepare a quote for you. And if agreed, or finance team will send you a purchase order and we will book a session for you. If you decide that the NERC route is your option, you have to take into account that you need to comply with certain requirements. The first one is to be eligible to be a PI at the moment of the submission of your application. You have to be hired by any UK university, research council institution, or UK public sector research establishment. You need to be at research level or above, be a staff at band 6, or be a holder or research fellowship. Unfortunately, if you are a PhD student, you are not eligible, or if you're a research assistant, junior technician, or other researchers who are employed on certain projects, or holders of fellowship that were not awarded following open competition, you are not eligible. The option that you have is to ask your PhD supervisor or the PI of your research group to be the PI of the application. You can find more information in this link. Those are the areas that NERC found, and they are the atmospheric physics and chemistry, climate and climate change, ecology, biodiversity and systematics, geosciences, marine environments, polar sciences, science-based archaeology, and terrestrial and freshwater environment. More information in that link. There are two types of applications. The first one is one-day pilot project. this application can be submitted at any time of the year, and it's for small projects that don't take more than 8 to 10 hours of staff time, and they are assessed by the IMF research staff. And the second type is full applications. It's for projects that will require more time. We have basically 2 calls per year. Usually it's in May and November, and the submission deadline usually it's in April and October. And these applications are assessed by a steering committee. The next steering committee meeting will be on the 22nd of May next year, and the submission deadline is 5 p.m. on the 25th of April. The application form, either for pilot projects or full applications, it's on our website, and you have the link here. And right now, I will go through what you have to fill out to complete in this application. So there is a first part in which you have to write the project title and the PI details, and also provide a project abstract. Then you have to nominate up to 2 people to come to the facilities to perform the analysis. And then you can, in additional personnel, you can add collaborators or people involved in that project, but they won't necessarily attend the facility. If the application is part of the thesis, then the PhD student need to give a brief summary of the thesis subject. The section 8 is one of the most important sections of the application, and it's about the project description. In this section, depending which type of application, if it's a pilot project, you have up to 1 page to describe the project. If it's a full application, you have up to 2 pages. In this section, you have to provide a background of your project, the objectives, aims, and hypotheses that you are going to test. Then you have to justify the use of the ion microscope, why what you want to analyze cannot be done using a different technique, and then indicate how your results are going to test your hypothesis. In this section as well, you will need to provide some images of your sample. The second most important section of the application is the analytical requirements. Here you have to name the person you contacted in the facility to discuss your project, and you have to list the number and type of sample, and the total number of analysis, and also complete a table with the elements or isotopes that you would like to analyze. If a concentration, it's something approximate, the precision required, and what type of mineral phase you would like to analyze. If your project is approved, your SIMS time is for free. But if you require, for example, the samples to be prepared in-house and image, you should take section 10, but it comes with additional cost that is not covered by us. Then in section 11, it's about project timing. And you have to tell us when you would like to get your analysis. We will try to fulfill your expectation sometimes we have a very long queue and it won't be possible, but we will do our best. And then in section 12, you have to talk a little bit about your current research, if your project is related to a much bigger research. And the last section is just to provide some information to NERC about the type of research you do and if you have any funding. The common mistakes that we usually see in the applications and that sometimes make the steering committee to reject applications is, for example, that they don't talk to the facility about the analysis that they would like to do, and maybe it's not feasible. Timing, if you just started your PhD and you submit an application, maybe it's not quite the right time to do so. Samples not being collected. As I said before, you have to provide images of your samples ready to be analyzed. So if you just collected your samples, it doesn't make sense. Lack of images, lack of representative images of your targets, and type of images. I'm going to give you an example. Backscatters, they are beautiful images because they allow you to differentiate different mineral phases. But that's what you get on the SEM, and that's the image that you get on the ion microprobe. Quite difficult to try to match the backscatter image with what you see on the ion microprobe. But if you provide reflected images, you can see, for example, here that you have a rectangle mineral, which you can identify here, or that there is a small mineral here that you can recognize here. More mistakes. People forget to fully complete the table of elements and isotopes. They require a precision or accuracy that it's not possible to achieve. Forget to justify the list of elements or the use of the SIMs, or for example, the hypotheses that they would like to test are not clear or feasible. What happens when your project is approved? Well, the first thing that you have to do is contact with one of us. Usually you will get a letter of approval, and on that letter there is a person named as a first contact. You have to prepare your sample, and those are all requirements. So the mounts have to be 2.54 centimeters diameter and about half a centimeter thick. And you have to, if possible, you have to locate all your targets in the internal 1.5 centimeters diameter. There are different types of mounts that you can prepare for SIMS. You have the epoxy mount, and there are different types of epoxy mount. For example, a grain mount, you have your mineral concentrates that you start putting in lines in double side sticky tape, and you pour epoxy and find, and after polishing, you get this beautiful mount. You have grain mount, but those grains are pressed in indium, and you have this type of sample here. Thin sections, if you want to analyze melt inclusions or minerals in thin section, that's also possible. You have two possibilities. You can round the thin section to have the size, the 2.54 centimeters that I mentioned before, or you can drill the areas that you would like to analyze on that thin section, and then either prepare an epoxy mount or press those areas in. Of course, depending on the type of analysis, you may need to introduce some standards in your model. I'm giving you here some really bad examples of sample preparation. For example, here you have a grain mount in which there is a hole, a trench around the grains that cause some conductivity issues. In this one, you can see that during the SEM imaging, they burn the resin around the grains, and that can cause some conductivity issues as well. In this one, you can see that I think this is a Petra sample, and it's full of bubbles. Bubbles can cause issues, can cause a lot of issues. It will take much longer to pump down to the levels of vacuum that we need. So if you have a sample full of bubbles, it's better to fill up those bubbles with epoxy. Or as Keshan mentioned before, flatness is key in our samples. And here you can see a sample that it's not very flat at all. More information about sample preparation can be found in this link. And after you have prepared your sample, you need to have all the information needed. So you need to image your sample, and you will need a raw map of your sample to be able to drive around on the ion microprobe, and then different reflected light images at different magnification. Other useful images, apart from the reflected images, reflected light images that are essential, for example, secondary electron images, CL images, or backscatter. And just my last slide is about our the facility status. So, as Kishan said, we are excited to have a new instrument on our way. And the 1270 will be replaced soon, but it will be still operating until June. After June, we will have to take apart our instrument, and the lab will be refurbished, and the new instrument will be delivered in November 25. It will take 3 to 4 months to have it tested and up and running, and probably late spring 26, we will be open again. However, our 7F will be open and accessible during all this time. So if you want to use our facility, we are open.
Wonderful. Thank you both very, very much for that really comprehensive and excellent overview and talk. It's genuinely, this is such a useful tool and information for the community. It genuinely is. That was excellent. Thank you. I wonder, we have just some questions popping into the chat, and I'd encourage anyone, if they have questions, to put them in there. That's probably the easiest way. So the question is, what is the minimum size for an MI necessary to analyze carbon in the glass? What is the lower limit of MI size, melt inclusion size, that necessitates use of the nanosins for this analysis, please? Thank you. Thank you. Yes.
Shall I answer that?
Yep.
Well, the smallest size probably is about 10, 15 micron in the smallest dimension of the inclusion, because often they're not quite round. And if there is a bubble, then you can't analyze the bubble. So there needs to be enough glass that if they get smaller than that, the optics on our ion microprobe are actually not good enough to really see the melt inclusion. And it's also a good chance that you start hitting the sides. So yeah, so you need a melt inclusion of about 15, 20 micron.
Very good. Are there any other questions? Oh, we got a thank you. Very good. Just for people's information, I've put where you've put links in your presentations, I've put them in the chat so people should be able to access those, should be able to access the chat afterwards. And if you want, we can always put them in the description of the talk on MinSoc, on our MinSoc YouTube. For those that didn't catch it, you will be able to, this has been recorded and you will be able to play it back and pause it and share it with all your friends and colleagues on the MinSoc YouTube channel. If there are no other questions, I'm going to let everyone go, but I just genuinely wanted to say thank you very much. That was really very good and very informative. And we really appreciate your contributions to MinSoc and to the whole community. Oh yes, I think lots of thank yous popping into the chat now. Thank you very much. And for those of you that are interested, our next talk will be in January and we'll be circulating details shortly.